minutes, I'm just going to give you guys problems to work on. So it's like I'm going to try to squeeze lab days in where I can. And so we will do a combination of, I'll give you a separable differential equation. You'll write down the slope field. You'll solve the equation and make sure that your solutions go with the slope field that you wrote. And then I'll have some more sophisticated ones to make sure that you can exercise some integration muscles you haven't used in a while. So a really key tool that you may have ignored in the past in a lot of applications in this class and other classes is partial fractions. So I'm going to make sure, I'm going to guarantee that all of you are masters of integrating by partial fractions. So for now, though, we are doing section 1.4, which is called separable differential equations. So a separable differential equation is a differential equation that takes this form. Definition, say a differential equation is separable. Okay, I guess I should add here, this is a first order technique. So a first order differential equation is called separable if it can be written in one of two equivalent forms. dy dx is equal to f of x times g of y. So that is to say, when I write it, when I solve it for the derivative term, the function on the other side of the equation can be separated into a pure function of x times a pure function of y. So it factors into a function of x times a function of y. Oftentimes this is written p of y dy dx is equal to q of x. These are equivalent, of course, because if you can factor the equation, you could just divide both sides by g, and you would get something in this form. Okay. So separability here refers to the fact that I can, that I can take the function on this side and I can break it into two pieces. So for example, this equation, dy dx is equal to yx plus yx squared over y squared plus 1 is a separable equation. It is separable because I could write this factored as the function y times y squared plus 1 times the equation x plus x squared. So it factors as a pure function of y times a pure function of x. So that is separable. There's another family of equations that live in the linear land that are not separable that we'll solve with a different method called integrating factors next week. Here's an example. So if I wrote down dy dx plus 9y is equal to x, and I try to solve this for dy dx, so dy dx is equal to x minus 9y, that is not separable. I can't take that and factor it into a function of x times a function of y. So separability requires I can do this sorting step where I have everything with respect to y on one side of the equation and everything with respect to x on the other. But now, for nothing more than the amusement of it, I'm going to tell you the theorem that tells us what the solution is, and then I'll tell you how everybody actually does it in practice. So a lot of you have seen this method before in earlier classes, I think. So what the theorem says is the following. If we have a differential equation, has the form p of y dy dx is equal to q of x, then by clever use of the chain rule, you can show the general solution is the integral of p of y dy is equal to the integral of q of x dx plus c. That's what the theorem says. Every separable equation has a solution, and I get it by just integrating p and setting it equal to the integral of q plus c. And I'm going to point out here that when we're doing these, a lot of times the function that we get out the other side I may not be able to solve for y as a function of x. I could get complicated expressions in y over here. So the cop-out when you're doing these, if you don't want to find y as a function of x, is you just write that this implicitly defines or implicitly solves the differential equation. So when I write that, what I'm saying is I'm not committing to finding y as a function of x. A lot of times that won't be possible. Now, that's the theorem that says what the solution is, and literally nobody ever has memorized that. Instead, since everybody in here is some kind of engineer or computer science major or something, even though secretly we all know that, well, okay, I should say, even though mathematicians tell you dy dx isn't a fraction, don't treat it like one, everybody knows the only reason we use fraction notation is because they're really fractions, and if I want to multiply by dx, I'm damn well going to. So I'm going to write down a differential equation that's separable, and then we're going to solve it. So if I wrote down something like dy dx is equal to, what would be a fun one to do here? Let's do that one. y squared plus 1 times x squared plus x. Here's what the actual method is. First, I'm going to sort this thing into a side with all the x's on it and a side with all the y's on it. So I'm going to write this as, okay, if I divide both sides by this, I'm going to get y squared plus 1 over y dy. And then because it's a fraction, I'm going to multiply both sides by dx to get the dx on the dx side of the equation. So a lot of times people call this the sorting step. So we sort it into a y side and an x side. And I'll point out, this can actually be made rigorous. And this should also remind you of the vector field stuff that we did in 241. This is like a pdx plus qdy sort of setup here. Now, when you're staring at something like that, you got differential expressions with dx's and dy's, what would make the dx's and the dy's go away? Well, just slap an integral on there, right? I mean, after all, if these two things are equal, I should be able to integrate them. And look, they're already set up. So what if I just so now I'm going to integrate. And really, it's like the slap on the integral step. So I'm going to write down the integral of y squared plus 1 over y dy is equal to the integral of x squared plus x dx. And then the next step here is hope you remember how to integrate. Hope you remember how to integrate. And also implicitly in that hope is that your professor's written a problem that you can. So of course everyone in here knows how to integrate that, I'm presuming. So I'm going to split the fraction up here. I'm going to split this integral up into the integral of y plus 1 over y dy is equal to the integral of x squared plus x dx. And that's going to get us y squared over 2 plus the natural log of the absolute value of y is equal to 1/3 of x to the third plus 1/2 of x squared plus c. I only need one additive constant here because if there were two arbitrary constants, I could just stick them together. And when you're done, you could look at that and think, can I solve for y as a function of x here? Am I ever going to be able to isolate y? And then you look at it and go, I've got a polynomial plus a transcendental function, so no, I'm done. And so if I want to finish the problem with no more work, I would write implicitly solves the differential equation. Implicitly. So a numerical solver would happily draw curves of that thing for you, right? It'll draw what these pictures are supposed to look like. And it's worth asking yourself at this point too, did I really get that much more information out of this numeric thing that has to be solved in a computer numerically versus the original differential equation where I could draw the slope field? I mean, what did I actually gain? Fine, that's the solution curve, but did I gain much from that? So in practice, most people who work with differential equations work with them at this level, and the computer just generates the curves. And very rarely are you working with explicit solutions, or even these implicitly defined solutions, because you have to use computers to study them anyway. All right, now I promised some partial fractions. So let's do a partial fraction problem. Questions about this one? This technique is supposed to be really straightforward, and for a lot of you, review, I think. All right, so let's look at something with a little bit more meat to it. Just a little bit. So last time, I think I wrote down the logistic equation dy dx is equal to y times 10 minus y. This had the slope field that looked like this. Here was y was equal to 0. Here was y was equal to 10. I think when we wrote the solution curves to this down, they looked like this. So if you were between the two asymptotes, you came towards this one. If you're below y equals 0, your behavior was this. If you were above y equals 10, then you were sort of pulled into the asymptote. So you can imagine an explicit solution for this problem is probably pretty complicated, right? Because there's 3 really different behaviors that are happening depending on which parts of the asymptotes you're on. So we should not be surprised if there's an absolute value involved in the answer, right? Because there's a range of values where something has one behavior and then ranges of values where it has really different behavior. So that's something to keep in mind. Of course, I know that going in because I know that's going to turn into natural logs. Okay, so that is a separable equation. We didn't do this last time, but let's actually see if we can solve it. This is a separable equation because it's dy dx is equal to 1 times y times 10 minus y. And this is a pure function of y. And that 1 right there is a function of x. It doesn't have to have an x in it to be a function of x. So using the sorting trick, I can rewrite this as dy over y times 10 minus y is equal to 1 dx. So that's our sort step. I slap an integral on both sides because that's just what it's begging me to do. So I'm going to integrate it. I'm going to take the right-hand side. So we get x plus c. And on this side, we have dy y times 10 minus y. And here's where I get to remind you that the technique of partial fractions exists, that you're obligated to know how to do it, that it is, and you won't have any context for this yet, but for any of you who are going to go into any field that involves the Laplace transform or signals or control theory, these are core type of things that show up in those fields. So being able to work with partial fractions is actually a core technique, which is part of the reason to practice it now. So this is a partial fraction problem. Over here and do some partial fractions. I will remind you, for those of you that need a reminder, since for a lot of you it's been more than a year since the last time you did this at this point. 1 over y times 10 minus y factors as a over y plus b over 10 minus y. Partial fraction step. This is a simple one because we have linear terms that are not repeated. If you guys want a more complicated exercise later, I can give you one where there's an irreducible quadratic down here or repeated terms. Some of you didn't even learn that the first time when you learned it. If you learned it in AP class, depending on your teacher, you may not have learned anything other than this case. I will remind you that the way to solve this is you clear denominators. And then if you want, you could expand and compare coefficients, but it's actually much more efficient just to choose convenient values of y. So I'm going to choose the value. This holds for all y, so I'm going to pick y is equal to 0, which gets me the equation 1 is equal to 10a, and so a is equal to a tenth, and y is equal to 10, which will give me the equation 1 is equal to 10b, and so b is also equal to a tenth. And that means that we're integrating not, if we want to do the integral of dy over y times 10 minus y, this is equal to the integral of a tenth over y plus a tenth over 10 minus y dy. So we split, which is going to get us log terms. So if we come back over here, this is going to be equal to 1/10 times the natural log of the absolute value of y minus a tenth times the natural log of the absolute value of 10 minus y is equal to x plus c. If you wanted to, you could stop here and say this implicitly defines a solution to the differential equation. If you guys have ever seen the logistic equation before, this is not where the derivation stops. In fact, you can continue this to find y explicitly as a function of x. The way to do that is to remember that I can combine differences of logs if they have the same number in front as a quotient in the inside. So that this is a tenth times the natural log of the absolute value of y divided by 10 minus y. The reason I'm working through this algebra is not because it's hard, but because there are things that show up in differential equations I want you to be aware of. If I ever multiply an arbitrary constant by something that turns it into another arbitrary constant, a lot of times it will just keep calling it plus c. So if I multiply both sides by 10, I'm going to get the equation, the natural log of y, 10 minus y, is equal to 10x plus c. This c is different than that one, but it was arbitrary, and I didn't know what the first one is, so I still don't know what the second one is, so I might as well just call it plus c. Now what should I do? E both sides. I don't actually know a more formal name for this other than e-ing. So I'm going to e both sides. We will eventually end up with a plus and minus because, not yet, but when there's still absolute values here. I'll show you where the plus and minus shows up. Okay, so you continue. E-ing both sides gets us the absolute value of y over 10 minus y is equal to e to the 10x plus c, with the observation that e to the 10x plus c is the same as e to the 10x times e to the c. And if c is an arbitrary constant, so is e to the c. So now we've got the absolute value of y over 10 minus y is equal to k times e to the 10x. And now we pick up the plus or minus sign if I want to go further. Because I can drop the absolute values, but to do so, I need to pick up plus or minus k. And then I'll leave it to you at this point. You can actually continue with algebra here by multiplying both sides by 10 minus y and then factoring. You can algebraically solve for y. And I think you end up something like y is equal to 10k e to the 10x divided by 1 plus k e to the 10x, I think turns out to be the answer. If you've learned the logistic equation before, this is what you learned, some kind of model that looks like this. So now the question that you should have here is, when we went through the process of doing this, am I actually getting all that much more information out of this?
Wait, is it plus or minus that stuff?
Yeah, I mean, the plus or minus shows up here, I think, right? Because the plus or minus was here. I dropped the plus or minus when I did this because I wasn't actually trying to show you what the real picture was. If there's no plus or minus, that's what gets you the internal behavior, I believe. So I guess the idea in this question is when you're working in practice, and this is an important thing to think about differential equations, I can write this down, but am I really getting more information out of that than I got out of this? This is easier to read. It's very obvious what the behavior of this thing should be off of the slope fields. A computer is perfectly capable of computing these solution curves. Am I really getting that much more information, if I'm working numerically anyway, out of this than out of that? And in practice, the answer is no. In practice, when you're working with differential equations, being able to write an explicit solution to a differential equation is significantly less important than being able to understand how the differential equation is determining the solutions. So there's actually not many of these that it turns out we can even write an explicit solution for. So of course, the very first question you get, like in any math class, is this going to be on the test? And the answer is, I mean, if you solved this equation and you stopped here and said this implicitly defines a solution, you would be correct. The algebra step at the end is not meaningful in a calculus class or like a linear analysis class. Okay, so that's all I want to talk about. And the rest of the class, I was just going to give you problems to work on. It's like, this is it. I mean, a lot of professors don't even do this section. It's like, oh, you already learned it back in 142 or whatever, except you guys didn't have 142 here. So I was just making sure that we've all seen it before. So what I want you to do for the rest of the class, I didn't print this because I didn't have time. but I will typically be printing these and putting them up online for lab day, and I'm putting it in the video as well because I want people to be able to review these questions. I have 4 questions to work on. So question 1 is going to be, I give you the differential equation dy dx is equal to minus x over y, and I want you to plot a slope field using isoclines. A, B, solve the equation using separation. So the method we just talked about today. And then C, actually make sure that your solution curves fit the slope field that you drew. Plot some solution curves. Question 2, do the same thing, but now do it for positive x over y. Same exercise. And then I have some more computational questions to think about. Question 3, just solve, let's see, here's one, was it x squared plus 1 y double prime minus y squared is equal to 1. So that's just solve. It's y prime, not y double prime. And then exercise 4, I will check the book because exercise 4 is how much partial fractions do you actually remember? So here we go. This is going to be dy dx is equal to x times y squared minus 1 over 2 times x minus 2 times x minus 1. Solve. Don't worry about slope fields for these guys. All right, that's it. The rest of the time is yours. Solve your questions, practice some stuff, and again, we'll pick up probably a method you guys have not seen before on Monday when we talk about integrating factors.